So let's remember our goal with this series of videos to demonstrate a 1930s station that would be considered portable. With the receiver, which we know is a regenerative receiver, it's always battery powered with the batteries inside the shielded enclosure. This is because power for the transmitter, usually at this time period, especially portable power, was always dirty. And by that I mean it was usually a rotary machine off a battery, and that meant there was sparking and arcing. So the receiver remained battery powered all through the 30s for portable operation. This included aircraft. In the aircraft they would use battery powered receivers just to isolate themselves from the dynamotor or the generator that's keyed to the aircraft's engines and keep the dirty power out of the receiver. So let's take a look at our transmitter so far. We're going to need a power supply for this transmitter. And of course, I'm looking at a couple hundred volts. Now, how many 9-volt batteries would it take to make 200 volts? And it's going to get kind of ridiculous. You start to buy 20, 25 9-volt batteries, it gets expensive as well. And for the purposes of a video, or even a transmitter that you keep in the closet, I don't think buying 25 9-volt batteries makes a lot of sense. So instead I'm going to make a fake battery, a faux battery if you want. And it will be based on a drone battery, a rechargeable lithium-ion, small battery, probably a couple thousand milliamp hour type battery. And that battery will be driving some type of converter that will increase the voltage up to a couple hundred volts. It also will supply a low voltage to light the filaments. So the transmitter is on a dirty power supply. It's a battery power supply, but it uses some type of converter on board. I'll even dress it out so it looks like a B battery. It can also supply the A battery, so it's a combination A and B battery. Now, if that battery is inside the case, which is where I want it, I don't want it external. If it's inside the case, we need some way to recharge it. So that meant I need an extra connector. So as you can see, I've drilled another connector in here. That connector is purely to recharge the lithium-ion drone battery that's going to be powering this thing. So that's going to be part of the circuit, the actual power supply that's inside the transmitter. So welcome to part 3. This is part 3 of the 1930s portable type transmitter. We're going to be taking this to the field and doing sort of a Parks on the Air Civilian Conservation Corps style, CCC Camp style, Parks on the Air with all portable battery operated equipment. So let's take a look at how the schematic has developed since the last video. First of all, I've added a bunch of switching here, and the first switching I want to go over is for the meter. I originally was going for a 30 milliamp meter, but then I saw that the current drain was higher and I didn't want to be damaging the meter, so I went all the way to a 100 milliamp meter when it's in this mode. I returned the 300K resistor, which gives us the 0 to 300 volt scale on the meter. The other switch over here, the operate and tune lamp, basically you can put it in the lamp position and you can monitor the current going out to the antenna. So it's a tuning aid. And then we have the transmit TR switch so that we can send signals over the receiver when we're in receive. And then I had a spare contact, and I think I'm going to use that for activating the high voltage on transmit only. That's coming a little later. In review, I did have to use the two 2.5 millihenry chokes. My homemade choke, I got kind of out of patience with that. I probably could have made it work if I kept at it, but I stopped and put some chokes in there just for getting us on our way. I broke a big rule with amplifiers, oscillators, and so on. You're not supposed to ground the capacitor rotor and ground the center tap. You either ground the center tap with a bypass capacitor, or you ground the rotor and you feed the center tap with a choke. If you don't do it that way, the push-pull circuit doesn't work. And in all the circuits they show doing it the correct way, but they don't really explain why you have to do it that way. You just cannot ground both sides. You either have to have a capacitor across the whole thing floating, or you need to use a grounded rotor type capacitor differential and feed this with a choke without the bypass cap. Those are your two choices with a push-pull oscillator or amplifier. I have included the second tune circuit, which gives me really legal output. If we were to simply feed this into a random wire, it might encourage harmonics. Of course, a push-pull oscillator naturally rejects the second harmonic. That's a big feature of this transmitter. The Jones doesn't have a big second harmonic because it is a push-pull circuit. That's another reason that the Navy decided to use push-pull circuits very early in the game in the early 1920s. But the added tune circuit we have here as our antenna tuner, in effect, is giving a lot of rejection to harmonics, and it also allows us to tap up and down this coil and get a perfect match into the type of antenna that we're going to use. Are we going to use a high Z antenna like a end-fed ZEP, a long wire half wave, or are we going to take a 50 ohm low impedance tap drive coax, or something in the middle like 300 ohm twin lead or a 300 ohm offset feed on a Windom antenna? So that's bringing you up to date on how the schematic has developed, and I think we are going to get into the build and the wiring of the circuit next before we put it on the air. Okay, so I've been mounting things to the front panel. It doesn't look too bad. Some of the holes, of course, had to be enlarged, but everything's pretty much where I wanted it. Excuse the vintage sideband net is on the air in the background. I have rotated the output coil by 90 degrees so that we have no cross coupling between the output, the oscillator tank, and the antenna tuner tank. So these are now at right angles to each other. I rotated this particular ceramic socket. That allowed me to get those in properly. I have, white porcelain and plastic here mixed. Hey, that's what was in the junk box. So at this point, I'll be just checking to see if I'm ready to begin the final wiring. But I am making progress on the transmitter, and very excited to get this transmitter finished. And of course, then we are going to get into the power supply part of this. But there's a long way to go before that. Looking at the front panel, of course, we have the 2 meters up top. I've got the on-off switch, which works with this rheostat, and that's going to control the filament voltage, the crystal, the key jack. This is the oscillator tuning, and this is going to be the antenna tuning control. This is the transmit receive switch, TR. And these are the receive terminals over here. These are the transmit antenna terminals. I have a light bulb that's used as a tuning indicator, and it can be switched out so you're not wasting power in the bulb. This particular connector had to be added to the front. Remember, since you're dropping everything into a case, you don't want to be drilling the case itself. You want the transmitter to be completely intact and functional outside the case, just sitting on the bench like this. There will be a battery inside this radio. The case is big enough to have plenty of room for the A and B batteries for this transmitter. So the idea of having an external power pack with a bunch of connectors and jacks like they did on that aircraft type transmitter that they made into a dog sled transmitter, I wasn't going to do that. I wanted to put the power supply on board. Now the power supply could be made of 20 or 25 9-volt batteries for the high voltage, and a couple of C cells for lighting the filaments. No problem. But I would rather use a modern battery that's rechargeable and produce the high voltage, and maybe hide it in a box that looks like it's a B battery. That way I have a battery that can be recharged, taken to the field, and I don't have to worry about it. So that meant I needed an external connector of some kind to be able to recharge the battery without having to take the whole unit apart again. So I have added an old phenolic type connector to the front panel of the receiver, and this will allow me to recharge that battery safely from the front panel. But as you can see, you got the silver showing because when you drill a hole, you're going to get something like that. But that's okay. Now I think I'm ready to start the wiring on this transmitter. Looking at the back, you can see that we're going to need, to move things into the proper orientation. That guy got cocked around, so that's got to be fixed. But there's probably another grommet hole that has to be made to get all these wires down into the chassis as required. And of course, this is where the batteries will hook up, or the fake B+ battery. I'm hoping with one rechargeable lithium cell that I'm going to be able to do everything, but if not, I'll have a separate system for the filament. But I think I can do everything off one battery, and I've got a very clever idea to make the high voltage. You may be much more interested in that than you are in this old transmitter. So the first step is to figure out if the rheostat has enough range to put 120 milliamps into the two tubes to light them up with either 3 volts or 5 volts. 3 volts if we were using 2 C or 2 D batteries to light the tubes. 5 volts if we were producing 5 volts from some type of regulator. So this is the 5 volt test, and as you can see with the rheostat all the way down, I've got 90 mils with 5 volts, and with it up here around 11 o'clock I'm getting into the 120, so no problem at all with 5 volts. Now I'm going to reduce the voltage to around 3 volts, and let's see if we can get up to 120. Great. Yeah, at 3 volts I still have range on my rheostat, so the rheostat's a good value. Looks like we're okay here for the rheostat test. So that'll be hooked right in series with the 3 or the 5 volt input. Okay, so here we are at our 120 milliamps, and we're reading 2.5 volts as expected. Not very much deflection for 2.5 volts on this meter. This is a 15 volt meter. I think I may use the meter to look at the actual battery input if I end up making a 12 volt based input type system. That way in one position I can look at the actual filament voltage, and the other position I can look at the battery supply. That's a nice meter. I can use that in 2 ways as well. The other meter I'm using in 2 ways. I'm measuring the high voltage as well as the plate or the cathode current. Next I'm adjusting the shunt on the 0 to 300 volt meter. With the 300K resistor removed, it looks like it wants a 1.22 ohm resistor so that we get 20 milliamps showing. This seems pretty good. So now with the 300K we have 300 volt meter, and with a 1.22 ohm resistor, and that's made of a 1 ohm and a 0.22 in series shunt, we have a 0 to 30 milliamp meter. Okay, so far so good. Key down around 180 to 200 volts DC. I'm getting 4 watts out. That's not bad for the untuned output. No loading control. About 60 or 70 milliamps on the meter. I've changed the meter to a 0 to 100 milliamp meter because it was drawing more current than I anticipated. With 2 tubes, of course, the current doubled. So about 67, 68, 70 milliamps of current. And again, key down, we're just under 200 volts. So she is working, and the tuning indicator is working pretty well, although it does change the loading. It keys a lot better with the tuning indicator out of circuit, as you can imagine, because the lamp is heating up and changing the loading as it heats up. But it's a very good tuning indicator. You can really tell you're getting fire in the wire, so to speak. Now I have the output on a low tap on the output coil, of course, to match 50 ohms a little bit closer. If we were doing a long wire antenna, I'd go all the way to the top of the coil. And the problem there is the light probably wouldn't light properly. So I'm still considering how to handle the light. I'll see if the tuning indicator works at higher impedances, but I doubt it does. It sure works great at 50 ohms though. So the tuning indicator was kind of a wag to see if I could really tell what's going to the antenna without resorting to an SWR bridge and so on. They were using indicators like neon bulbs and incandescent bulbs as tuning indicators at the time. I suspect if we had a half-wave antenna and we're coming off the top of the output tuner coil, that a neon bulb would be the correct way to tune the output. For a low impedance tap, like I'm using into 50 ohms, the incandescent bulb works quite well. Let's turn the set on. Okay, so we turn the set on, you can see that the tube's lit up. I'm going to look back there to see if things are overheated. No, everything looks normal back there. Now let's turn on the high voltage power supply. And the tuning indicator is in line right now. As you can see, as you tune, can't really dip the plate with an oscillator, okay, so that's not what that ammeter is for. And right now this is set as a 0 to 100 milliamp meter. Remember I had it 0 to 30. 0 to 100 gave me a lot better range to look at. Now once you are tuned up, and the output of course is a little touchy because that capacitor is pretty big. Once you've got the thing tuned up, switch the indicator out. Immediately the tone improves and you're almost up to 3 watts. So I imagine on a little bit higher voltage, voltage over about 150 volts, we might be able to get this thing to put out 4 watts with a pair of type 30s. Not the most perfect tone, but of course that's going to vary with the crystal as well. So about 190 volts key down gives about 3.5 watts. So I think my goal is going to be a 200 volt power supply, and we can expect between 3 and 4 watts out with most of these crystals. I've been testing a whole bunch of crystals with it. Seems like 3 to 4 watts is the maximum on this transmitter with reasonable power without overdoing the tubes. As you can see, I have the resting voltage up at 250 volts. But under load it goes down to 200. So a well-regulated 200 volt supply should be adequate. These tubes do have a maximum plate voltage of 180 volts, but as you can see we're exceeding that by 30%. It doesn't seem to be hurting the tubes at all. So a couple of nice little contacts, both of them near vertical incidence where the signals were within a couple hundred miles. That's exactly what we're looking for with the transmitter. Remember, the receiver is going to be the regen, and the regen is powered with its own internal dry cells. What about the high voltage for the transmitter? How do we make that portable? Rather than buying 20 or 25 9-volt batteries and making a B pack, and packaging it up like I did with this folded box that I made with my printer, making a fake B battery, I've decided on the next video, we're not going to go to the field in the next video. We're going to develop the power supply for our battery system inside the transmitter. And I've got a small drone battery, a set of these drone batteries. These are 2200 milliamp hours, basically 12-volt cells, lithium ion, and I've got a little 100-watt AC inverter. This takes 12 volts and converts it up to 120 volts AC, 60 hertz. Now, if we put a diode bridge on this and a capacitor, it should get us up to around 160 volts DC. That will certainly run the transmitter, probably a couple watts, no problem. We could go that way. Or possibly we could use a voltage doubler off this and then a regulator and get it down to that target 200 volts I'm looking for. Anyway, the next video is going to be about the power supply for the portable transmitter. After that, we'll take the whole thing to the CCC Camp and do a Parks on the Air Civilian Conservation Corps camp style. I'll probably be putting up an end-fed antenna like a half-wave long wire or an inverted L, something that's expedient, something that would have been used at the time. But that's going to be a couple more videos before we get to the field with the setup and see if we can actually make contacts with our 1930s station.